Okay, so good morning everyone. So last time we had done force balance and got an equation for an elastic rod. Now we have to do moment balance, just as we do in beam theory. So we are going to do moment balance. So let me just redraw the deformed rod. And you guys can recall that on this cross section, which is at S equal to S2, we have the internal traction acting, which are any little on a little area here, the traction would be, or the force would be P, the first pk E3 dA, and over here we will have negative of it because the normal is pointing in the negative direction. So minus P E3 dA. Okay, so that's S equal to S2, and then you have on the lateral surface the external tractions, which I guess we denoted by T external, and you also have the body force, of course, acting everywhere within the volume. So you could denote that by B. Okay, so we had done the force balance, so we want to do now the moment balance. So for moment balance we have to choose a reference point about which we will compute the moment. So let's take that to be the origin of the coordinate system itself. Okay, so we will do moment balance about the origin of the coordinate system. Okay, so we have, let's first get the moment of the external loads, which are the body forces and the traction on the lateral surface. So we are going to do moment about the origin. So let's do first due to external loads. Okay, so for the body force part, the body force is acting everywhere within the volume. So any point within the volume of the rod, since it's a deformed rod, we could denote that with little x. Okay, and maybe let's take it cross section wise. So here is your cross section, and a point on the cross section we denote by little x. So the body force that acts on this point will generate a moment of x cross B dV, isn't it? Where dV is the undeformed volume of a small volume over here, and then we do its triple integration, and we can maybe call it dV naught for the undeformed volume, V naught. Okay. But now we want to write this little x in terms of the center line position and the extra thing. So, you see this is your center line, and then you have extra vector. So, we could always write this as little r of s plus little x minus little r of s okay, cross product b dV naught. Okay, now what do you think, what is this equal to? Little x minus little r of s. So, that is the extra vector, and what would that be equal to? So, if we have to use our constraint kinematics for a spatial coordinate rod, then this thing is simply x alpha d alpha, isn't it? X alpha d alpha of s. However, as we said that we do not want to restrict to that constraint kinematics, because it makes our system stiff. So, there is some extra on top of this, there is some extra displacement u for warping, isn't it? So, let us just, so this was just to give a perspective. So, let us just forget about this and think that we have this thing. So, this is anyway general, right? Little x denoting the deformed coordinate of any point, and then little x minus small r is that extra vector, right? Okay, I hope I am not confusing you. So, please say again.
Shouldn't it, we also need the rotation?
Yes, so this is same as for spatial coordinate rod. This then becomes big X alpha, big R E alpha plus your U.
Well, last time we had the U also multiplied with R.
Okay, you can write that, sure. You can write either way, so this then becomes a different U, of course. Okay, since I did that, so maybe I will stick to what I used last time. So, this becomes big R of x alpha E alpha plus your little u. Okay? But I am not going to use this really in this derivation. I will just keep it as it is here. There is no confusion here, right? Little x denotes any point in the beam, and then I am just taking this difference. Okay? All right. So, then let us see what does this become. So, we are going to split it into two parts, as you see here, and again we take the outer integral for S1 to S2, and we could write this as small r of s cross integration over the cross section b dV naught plus Okay. So that was just due to the body force. We are going to have similarly term from the external traction. So let's also write that here. So that would become plus S1 to S2 and again my little x minus small r of s cross T external dA. So that's on the boundary. So this one again is split into two parts. We have one more term here, S1 to S2. Okay, could we write that? So you see the first term is due to the body force, the first line, and the second line is due to the traction on the lateral surface. And just as the first part was split into two, the second part has also been split into two, isn't it? And then you can further, as I am dividing this integral, this dv naught then becomes, this becomes the integral over omega naught, and here you have ds. Okay, rs ds cross. Is that okay? So dv naught has been written as ds d omega naught. Same thing you can do over here. So dv naught, so this becomes d omega naught, because this is an integral over omega naught, and your ds is sitting here. We do the same thing over here. So this becomes rs ds cross, and now you see what is this going to become? dl, integration over the peripheral line, dl. So you had the cross section over here, and you are just integrating over the boundary of the cross section. So that's your dl. And then you can do the same thing over here, ds dl. Okay, so and then we have to identify some terms. So if I write these two together, what does this become? S1 to S2 ds, and then you have r of s cross Okay, isn't it? So, I just wrote these two terms together and these two terms together over here. And can you identify what is this? We had defined it last time. That's your distributed load, right? So, this becomes integral from S1 to S2 ds then R of S cross n hat. Was this n hat or n tilde? Hat? Okay. So, n hat of S. Plus, and then you have to see what is this really equal to. So, we have to again define some new term here, and if you want to compare with beam mechanics, what do you think this would be? So, we have this term, for example, is denoting the couple due to body force about the center line. That is why the arm, see the arm of the force is x minus small r of s. So, that is the arm of the force. Then you take the cross product with the force itself, b d omega naught. So, that is the couple due to body force about the center line. Similarly, this term is the couple due to the lateral traction and again about the center line. So, in your beam mechanics, when you see you have distributed couple acting along the beam, so that comes because of these two terms. If you have a gravitational force, for example, the distribution is such that the couple due to it is 0, but you could have the distribution of body force. If it is not symmetrical, it could create a couple. Okay. Any confusion here about the steps that I have taken? Okay, you can interrupt me. So, this becomes S1 to S2 of ds, and then I will write this as m hat of S. Okay, so we are done with the external loads. Now, the internal loads are remaining. So, we have to find out moment due to internal loads. So, this was due to external loads. Okay. So, we first look at the S equal to S2 cross section and find out what is the moment due to those tractions about the origin. So, that is again going to be equal to integral over that cross section omega naught, which is at S2, right, the cross section at S2, and you have little x cross P E3 d omega naught. Right? And again we want to split it into two parts. This little x I want to split into two parts as we have done earlier, because in beam theory all the forces and moments in a cross section are about the center line. When we say about moment at a cross section in a beam, So, that is moment about the center of the cross section, not about the origin. So, therefore, we have to do that splitting here. So, this becomes little r of s cross p E3 d omega naught plus little x minus little r of s cross p E3 d omega naught. And then we come here, and what we see that little r of s, since it is independent of the integration being done here, it acts like a constant. So, you can take it out just as we have done earlier. So, we are
You said R is S2, no?
yes. So, this becomes r of S2 that is also r of S2. Right. So, this acts like a constant and it comes out of the integration just as it happened on the top, and this becomes r of S2 cross p E3 d omega naught plus this term. You see, I cannot take the little x out of the integral because it is varying in the cross section. And you can now see what is this equal to? That is our force on a cross section, right, that we had defined n of s. So, this becomes little r of S2 cross product n at S2, isn't it? Because this is force at S2, because we were integrating on the cross section at S2 plus, now you see what is this equal to? Can you guess what is this? So, this term here is the arm about the center line, right. Whenever we compute moment, we have arm and the force. So, this is the arm of the force about the center line, that extra vector cross with the force, and we are integrating in the cross section. So, that is going to give us the moment that we talk about, right. So, that we are going to define as m without the hat. So, you see it has very nicely split into two parts, r cross n plus m, and we did not have to use that restricted kinematics here. Okay. So, I did not say that x minus small r is equal to x alpha r e alpha. Okay. So, it is very general. All right. So, and similarly, you are going to get a term due to cross section at s equal to S1, right. So, this is s equal to S1, and when I combine all of them together, then what do I get? So, net moment is then the moment due to external loads, which is S1 to S2 ds of R of S cross n hat of S plus m hat of S plus this term R of S2 cross n of S2, and then you will have a minus R of S1 cross n of S1 plus m of S2 minus m of S1, right. So, I also included the term due to the cross section at S equal to S1. Okay, and then we will do as we did last time. So, this becomes S1 to S2 of ds, and then within, so I am going to write everything within the integral. So, this is R S cross n hat of S plus m hat of S plus R cross n prime. You see, because we have this minus this, I could also very well write it as R cross n prime and then integrate. You will just get the boundary term which are here, and same thing for the moment. So, this becomes plus m prime. Okay. Now, this part you can then split into two, use product rule. This becomes R prime cross n plus R cross n prime. Right. Okay, now you have to see, can some terms get cancelled? For example, look at this term and this term together. What does this become? No, not m hat, sorry. Without the m hat, yes, of course. So, can you see, if you combine these two terms, what does this become? R of S cross n prime plus n hat, but that is 0 from your force balance. The first equation was n prime plus n hat equal to 0, right. So, you can remove them. You know, similar thing happens even when you derive your angular momentum balance in continuum mechanics. You will have a term which cancels due to linear momentum balance, and then you get that the stress is symmetric. Same thing is happening here. So, what remains then is S1 to S2 ds so I will write it as m prime plus r prime cross n plus m hat of S. And since this was the total movement, this has to be equal to 0. And since this will happen for any section of the rod, S1 and S2 are arbitrary. So, this implies that the integrand within is also 0. So, this gives us the equation m prime plus r prime cross n plus m hat equal to 0. Okay, so here is your equation which you got from the moment balance, and of course this was simple statics. If you had dynamics also in it, you will have something on the right hand side, but let us not worry about that. And you also derived your force balance equation, which was n prime plus n hat equal to 0. All right, so these are the two equations. One, each of them are vector equations, and each of them have 3 in it. 3 plus 3, 6 equations. So can we talk about what's the nature of the equation here? Can we use this equation to solve our unknown kinematic variables? So for our special cross-rod rod, the unknowns are little r and big R, right? So little r and big R of S, these are our unknowns. So of course here we have 6 unknowns, little r has got 3 unknowns, and big R, as you saw your representation, if you use axis angle representation, it also has 3 unknowns. If you use quaternions, it has 4, but then it comes with an extra constraint. So basically it has 3 unknowns. So 3 plus 3, 6 unknowns, and you got 6 equations also. So equations are all there, but can we use these equations to solve for these unknowns? What do you think? Can we use these equations? No, right? Because these are not in terms of the kinematic variables. These are in terms of forces and moments. So it's like, in continuum mechanics also, the equations are in terms of stress, but your unknowns are the deformation map. So what do you do then? Any idea what should we do? So we need, of course, equations which can connect the forces and moments with the kinematic variables. What are those equations called? The equations which connect stress with the kinematic variable. Constitutive equations, right? So that's what we have to look for. Yeah. You see, these are known to you, by the way, n hat and m hat, because they are due to external loads. So these are sort of known to you. The unknowns are n and m, which you have to express in terms of the kinematic variables. So that's something it's not clear how those two are related to each other. Okay, so we'll try to address that now. Sometimes people would just use restricted kinematics. For example, over there, that little x, see that's your moment, right? Moment equal to that, and over there they will just say substitute that little x minus small r with capital R times x alpha e alpha. Let me just write that down. So they will say that m of s, for us it is integration over the cross section little x minus small r of s cross p e3 d omega naught, whereas n of s is simply integration over omega naught of p e3 d omega naught. Now if we use that kinematic, that deformation map, constrained deformation map, which is small x equal to little r of s plus big R of S into x alpha E alpha. If you use this, you take the deformation gradient. See, this is a constrained kinematics. Use this deformation map, take the deformation gradient, get your P from 3D constitutive law, right? P is equal to del W over del F if it's a hyperelastic material. And over here, this simply becomes big R times x alpha E alpha. So you can also use that and directly get your forces and moments in terms of the kinematic variable, isn't it? For example, you see, if you use this deformation map, constrained deformation map, what is then big F? That's going to be small r prime tensor product E3 plus big R of S E alpha tensor product E alpha plus big R prime x alpha E alpha tensor product E3. Then you can take your rotation outside and this becomes big R of S of big R transpose little r prime tensor product E3 plus E alpha tensor product E alpha plus big R transpose big R prime x alpha E alpha tensor product E3. Right? So that's, you see, this deformation map, deformation gradient is completely in terms of the kinematic variable and its derivative. Big R is there, little r prime is there, big R prime is there. So this is completely in terms of your kinematic variable, small r and big R. Why don't we put this deformation gradient here and get your P? Because P will be in terms of deformation gradient, right? From constitutive law, 3D constitutive law, you can always write your P in terms of deformation gradient. And then you integrate over the cross section and get your force. Similarly, you can do for moment. This arm simply becomes big R times x alpha E alpha. So you see, with the constrained kinematics, you already have forces and moments in terms of your kinematic variables. But as I told you, constrained kinematics are not so good. It's going to make your system rigid, and as it turns out, it does not even give you the simplest, it does not give correct answer even in the simplest case of stretching of a bar. You know, if you just think of a stretching of a bar, so we have a bar, you can do that calculation at your home. You know, you have a bar and you are just stretching it. And then try to think of in terms of rod here, what will be small r of S if you are just doing stretching. So stretching of a bar. So how does the center line change if you stretch a bar? If you have not stretched it, then it's simply SE3, right? It's along the axis SE3. But when you stretch it, let's say by lambda, it becomes lambda times SE3, isn't it? And what about capital R of S? are the cross sections rotating when you stretch it? It's not. So capital R is simply identity, a constant. Let's plug them in here and see what happens. Capital R is identity. What is small r prime? Small r prime lambda E3, right? dr by ds lambda E3, a constant. So you get lambda E3 tensor product E3 plus E alpha tensor product E alpha, and this term simply vanishes because big R prime is 0, since big R is constant. Okay, and as you can see here, this is same as lambda minus 1 E3 tensor product E3 plus the identity. So that's your E alpha tensor product E alpha plus E3 tensor product E3, then you subtract E3 tensor product E3. And so lambda minus 1 becomes your axial strain. Okay. So now you plug this deformation gradient in here, get your stress, and integrate that over the cross section to get your force. What do you think? What force should you get? For the case of stretching, what force should you get? So you have a bar, you strain it by, let's say, epsilon. How much is the force generated in the bar? It's a very simple case. What is it? Can anyone tell? You have a bar, you strain it by epsilon. What's the force in the bar? EA times epsilon, right? E is the Young's modulus, A is the area of the cross section. So this should then come out to be EA times lambda minus 1, isn't it? If a strain is very small, linear elasticity will hold, and it should come out to be EA times lambda minus 1. But when you put this constraint kinematics in here and integrate, you will see it does not come out to be that. So these two do not turn out to be equal. So that constraint kinematics fails even for the simple case. And that happens because the constraint kinematics violates the traction free boundary condition. You have a bar, and as you are stretching it, there is nothing on the lateral surface, it is traction free. But if you use this constraint kinematics, it will turn out that it violates the traction free boundary condition. See, this kinematics is not allowing the cross section to shrink as you are stretching it. So you are making your system stiff. Therefore, the modulus term does not turn out to be this, it will turn out to be higher than this number, EA. Okay? So that was just a side remark that this constraint kinematics does not give us correct modulus. So we don't want to use this, but there are developments where people use this kinematics to get your equations, get boundary conditions, everything, but when it comes to getting the moduli, they will just say, okay, let's just use the correct moduli. So that's where they do a little bit of cheating and just say, okay, just use the correct moduli, because it turns out it gives the correct equations. If you use this constraint kinematics, everything turns out to be correct except for these moduli. Okay? So, we are of course not going to use that, and we will find a different way to relate the forces and moments with the kinematic variables, and of course that way you are also going to learn some new techniques. Okay, so we want to talk about constitutive law, right? Constitutive equations. Constitutive equations. So, assuming that the beam or the rod is hyperelastic, we can always think of an energy function, right, which will give you the strain energy stored in the rod. Now, since we are talking about a 1D theory, the strain energy, this must be strain energy per unit undeformed length, not the strain energy per unit undeformed volume that we have in 3D elasticity. So, so we want to define phi, which is strain energy per unit undeformed length. And then we have to think about, or we have to postulate, what will this strain energy function depend on? What can it depend on? Now, since in our theory, for our special Coushatt rod, the unknowns are little r and capital R, which are the kinematic variables. So, therefore, for that particular theory, the energy would definitely depend on those kinematic variables. So, you can do any theory and the energy, you would then say that it depends on those kinematic variables. So, when you develop your own theory and when you come here, you will say that the energy depends on the kinematic variables and also its gradients, its derivatives. Now, just as in 3D elasticity, why do we say that W depends on F, the strain energy per unit undeformed volume? Why does it depend on deformation gradient? So, over there the kinematic variables are your deformation map little f and then its first gradient, which is your big F. You could have also taken the higher gradient. And then when you apply objectivity or frame indifference, it turns out that W does not depend on deformation map. So, it goes away. And when you say that I want to talk about simple elasticity, I do not want to talk about higher gradient elasticity, then you also drop this out and your W only depends on big F. So, these are some postulates. So, same thing we want to do here. So, that was for 3D elasticity. So, here again the energy function is going to depend on the kinematic variable and its derivatives, but now the derivatives will be only with respect to arc length, with respect to S, not with respect to the cross sectional coordinates. In any case, these only depend on S. So, derivatives will be only with respect to S. So, you have little r prime and big R prime. and you could of course take even higher gradients, but you have to stop somewhere. So, we stop here. Okay. So, then what is the next step? The next step is to apply the principle of frame indifference. So, now we want to apply what is called the principle of frame indifference. You see, just as in 3D elasticity, you have a body and you deform it, it gets some energy, and then if you further rotate the deformed body rigidly, the deformed body you rotate it rigidly, the energy does not change, right. You have any body, if you rigidly rotate it or rigidly translate, its energy does not change. So, the energy function must be such that it satisfies those physical experiments, isn't it. So, we want to do similar thing here. Okay, so maybe I will do it here. So, we have our undeformed rod, which gets deformed and maybe looks like this. Okay, so, this has got some little r and capital R. Let us further translate and rotate it. Okay. Keep this deformed rod, translate and rotate, okay, or rotate and translate, whatever you want to do. So, but we want to apply rigid motion. Let us apply rigid motion to this rod. Suppose that I translate it by t, translation vector t. Now, since it is rigid translation, it is a constant, it does not depend on s, it is a rigid translation, whereas these ones depend on s. Okay. So, translation and rigid rotation, let us say by q. So, once you do that, this will maybe look like this. Okay, so, it has simply rotated. So, it translates here and then rotates. So, you can also reach there through a different map. So, one way to reach here is first you apply this little r capital R, then you apply this rigid motion. The other way could be a direct way. So, but the thing to see is that in both the configurations here, the energy would be the same, isn't it, because they only differ by rigid motion. So, what is this new? So, I want to find out what is the new small r and new capital R here, which will directly map my rod over there. So, we have to of course think about it more carefully, what am I doing here. So, maybe let us say we first rotate by q about some point x naught. So, I will say first rotate by q about x naught, and in the second case, so you have done the rotation, then you translate by t. So, in the first case, when you rotate by q about x naught, so think of a point x naught somewhere over here, and I want to rotate this about this point x naught. So, any vector, so you have your so that is your center line, small r of s. Now, since you are rotating about x naught, this vector will not change its magnitude, right. So, this vector is simply going to rotate without changing its magnitude. So, if I write down your, so after the first step, what is my small r, let us say tilde, what is that going to be equal to? Can I say that this is same as x naught plus q times small r minus x naught? So, I am rotating it about the point x naught. So, you see this part corresponds to just the rotation of this vector, this relative vector, little r minus x naught. This is that vector little r minus x naught, which rotates by q and gives you this. And I am adding x naught because I am always measuring my position from the origin. So, this is that x naught. So, that x naught plus the rotated vector. So, this is x naught plus the rotated vector. Okay. So, that is just after the first step, and then you further translate by t, and then in the second step, when you translate by t, you get your final r, which is your r nu, and that is equal to this r plus t. So, this becomes x naught plus t plus q times r minus x naught. So, that is your final r, the one that we are looking for over here. How about your rotation? Let us think of rotation now. So, after first step, what does this become? So, you have a cross section which in this step has rotated by big R, and then this rod further rotates by Q. So, what is the total rotation of the cross section? So, there are two rotations here, one is by big R and then by Q. So, what is the total rotation? So, that is simply Q times R. So, that is in the first step. Then you do your second step, but the second step involves simply translation, there is no rotation. So, your R nu is same as R tilde, which is Q times R. Okay. All right, and then what is R nu prime? Maybe I'll talk about this while it is up there, and Prakhar cleans the board. Okay, so you see here, so you have gotten your new R, little and big r's, and then I look back at the energy function. The energy function in terms of your just little r and big R, and in terms of new r and big, and so new little r and new big R, it would give the same value, right? That's your frame indifference. The energy cannot change, right? So what's your R nu prime here? Because you have to get your R prime also there. What's your R nu prime? You just take the prime of this quantity. X naught is constant, goes away. T is a constant, goes away. Q is also a constant, you don't take its derivative. So only small r is there. So this is same as Q times small r prime. What about big R nu prime? What's that equal to? Q is constant, so I don't take its derivative. Q times big R prime. So when I apply my frame indifference, I will see that phi of a small r, comma big R, comma small r prime, comma big R prime is same as phi of a small r nu, comma big R nu, comma big R nu prime, comma big R nu prime, which is phi of that R nu over there, which is x naught plus T plus Q into little r minus big X naught, comma Q times big R, comma Q times little r prime, comma Q times big R prime. Okay, so we are almost there. So what should we do now? Can we get rid of some of the variables from here? What if we forget about rotation, rigid rotation, and just do translation? So Q becomes identity, isn't it? So in case of pure translation, this is phi of little r plus T, comma big R, comma little r prime, comma big R prime. So that corresponds to pure translation. And you see that you take any arbitrary translation, the energy has to be the same, which can only be possible if the energy does not depend on the first argument. Because you see, you take this first argument, you make this first argument anything, energy still remains the same. When can that happen? The function must be independent of the first argument. So we then get rid of this, because T is arbitrary. Since T is arbitrary, Okay, then we can think of simple pure rotation and we see what's happening. So that's phi if there is no t, just rotation. So that's x naught. Okay, first argument is anyway gone, so we are not going to write it. The second argument is qr, then q little r prime and q of big R prime. This is more tricky. Can we get rid of any term here? Yeah? No? Look at the second term. What if we take q equal to R transpose? It becomes identity, isn't it? So, what I am saying is that it does not depend even on the second term. Would you agree to that? Yeah, it's a bit tricky, but that's what's happening here. You can take any q and the energy has to be the same. You take q equal to R transpose, this becomes identity. So, phi of for any q and big R would be same as phi for identity here. So, again it is independent of your this variable here. You take anything here, it finally only depends on identity. But these ones are, you can't get rid of these ones. Can you now see that? Can you make it a constant? That's the thing. See, this variable over here can always be made a constant. Whatever is big R, you can always take q equal to R transpose and make it a constant. But here it's small r prime. You cannot take q equal to small r prime or something to make it a constant. All right, so this definitely goes away. And what about these ones? Do you remember what you do for W of f, then becoming W of u? F is equal to R u, then you get rid of R. So, something like that we have to do here. And you can show that this take q equal to R transpose and it should only depend on R transpose little r prime and big R transpose big R prime. So, these are basically your invariants. These are the invariants which do not change due to these rigid motions. For example, if I try to find out what is big R nu transpose into small r nu prime, let us try to find this. What is this equal to? So, now, big R nu is q times big R. So, big R nu transpose would be same as big R transpose into q transpose. What is R nu prime? R nu prime is q times small r prime. You see these two go away, q transpose q is equal to identity because it is a rotation, and you get big R transpose little r prime. So, what you see is that this combination does not change when you apply rigid rotation and translation. So, this is a frame indifferent quantity. Same thing you could also do, you can also show for big R nu transpose times big R nu prime, what you have here. What is this equal to? This is big R transpose Q transpose times big R nu prime, that is equal to Q times big R prime, which is same as big R transpose big R prime. So, what you see is that these quantities do not change due to rigid translation and rigid rotation. So, as a result of this frame indifference, what you have found out is that this phi would be such that this would be same as some other function psi of big R transpose little r prime comma big R transpose big R prime. Okay, so, we have reduced from 4 variables, 4 arguments to 2 arguments. Okay, so, that is the result of frame indifference. And of course, you would also try to think of what is the physical meaning of these terms. These are your strains, as I will show down the line. These are the strains of our rod theory, and they have got some physical meaning. So, we can try to find out the physical meaning. Okay, so, let us say or define V equal to big R transpose small r prime. So, that means your small r prime is same as big R into V. Okay, so, I am defining a vector V like this, and if you write your V equal to V1, V2, V3, which is same as Vi Ei, then your r prime is same as r times Vi Ei. Then you dot it with Ej on both the sides, and you get r prime dot Ej is equal to big R Vj. Is that correct? I think I missed out something.
The EI is already gone with the R.
EI, no, there is something. Oh, I can't just do this, because this is with R times EI is together. I can't do that. Okay, so that was a mistake. R prime. Yeah, okay, yes, that's true. So, I have to make it with Di. Yes. Can this somehow be gone? Okay, so your R prime, I am writing it as big R Vi Ei. but this is also same as Vi di. See your directors, right? Di is big R times Ei, the local basis directors, which would mean that your Vi, now you can take dot with dj for example, and you can show that, why don't I do it instead of telling it. So let's dot it with dj, and that's going to give me r prime dot dj is equal to Vi times di dot dj. Now what is di dot dj? Directors are all unit normed and perpendicular to each other in this theory. So di dot dj is same as delta ij, so this becomes Vj. So you see what's the meaning of this? So you have your r prime vector here, and think of the local basis. So let's say this, that's a cross section. So that's your D3, that's your D1, and then your D2. So the component of R prime along the directors, those are your Vj's, isn't it? So it has got some meaning. So you have to resolve your tangent vector in the local basis, and that's why this quantity did not change. So why is this not changing when you rotated it? Can you see now? If you rotate this, your r prime is also rotating, directors are also rotating, they are all rotating together, so that the components do not change. So therefore this was a frame indifferent quantity. So Vi's are all frame indifferent. And what's the meaning of V1, V2, V3, for example? If I want to find out the meaning, so I think that can be seen if I use the fundamental theorem for this derivative. So your Vj is small r prime dot dj. Now small r prime would be same as limit epsilon tending to 0 r at s plus epsilon minus r at epsilon divided by epsilon dot with dj. So think of your rod here, and suppose this is the point, this is S, and here is a point S over here, and another point S plus epsilon. So we have our origin somewhere. So this is your R of S, and this would become your R of S plus epsilon. Let me make it more prominent here. So the difference of these two, that's the difference. That's your small r of S plus epsilon minus a small r of S. And then I want to take its component along the directors. So suppose here is your cross section. and this is your, so this is this, that's your D3, that's your D1, and then your D2. I'm not sure if I can make it good again. It might turn out to be equally bad. So, all right. So here's my small r of s, and that's your small r of s plus epsilon. And this difference is small r of s plus epsilon minus a small r of s then we think of the cross section here. And its normal could be, okay, I have to make it a little different. We suppose that's the cross section, and its normal is like this, D3, that's your D1, and that's your D2. Okay, and you see what's on the denominator. The denominator is, I take the projection of this along D1. Let's say I want to do it for j equal to 1. So, V1, which is r prime dot D1. So, I want to take the projection of this along D1. And here is your cross section. And then you take the limit. So think of what would happen as epsilon tends to 0. And you are, for every epsilon, you are taking the projection along D1. First of all, just think of what's the projection equal to. So you take the projection, and this is that projection, right? Isn't it? So what's just telling you? That's the shift of the two center lines along D1, right? What's the shift in the two center lines along D1? Now, as epsilon tends to 0, what is that going to give you? Can you relate it with some strain? Isn't that the same as, of course, because it's also taking the derivative is this, sorry, I am also dividing by epsilon. So it's giving you some rate of shift. And as epsilon tends to 0, it's telling you the rate of transverse shift. So you have two cross sections, the rate of transverse shift. What is that? What is that? Can you tell it? Transverse displacement. What do you call it? Yeah? Shear, right? Yeah. So that's the shear. So this denotes your shear. Shear along D1. V1 is the shear along D1. Similarly, V2 is the shear along D2. And what is V3? Likewise, you think of V3, that will be projection of this along D3. So, in the limit epsilon tending to 0, what is V3? It's the normal stretch, right? Axial stretch. So, V1 and V2 denote shear, and V3 denotes axial stretch, and when you subtract 1 from V3, you get axial strain or normal strain. All right, so I think I'm already running out of time, so we'll continue in the next class. We'll also understand what's the physical meaning of the second argument over there, big R transpose, big R prime. You'll see they contain the information of curvature, bending curvature and twist. Okay, so see you in the next class, Friday.